to cyber, and so thank you for bringing that to us and talking with us about it.
Thank you so much. Anybody here a Penn State fan? We are. Come on, again. We are. All right. So, we are a team from the College of IST. I'm just the mouthpiece, but we did this together. The title of my talk is Bits Are Bullets and Barricades, the Real Nature of Information Warfare. Which button do I use?
Oh, down is forward.
Down is forward. There you go. Okay, who knows at least one person here? Hands. All right, 2, 3, 4, all 4. All right, good. Well, we're going to talk a little bit about each of these people here. I like to go from first principles. First principles and foundations are really important. Knowing where you're coming from helps you know where you're going. Max Planck, one of the fathers of quantum physics, at the very fundamental level of the universe, at the fabric of the universe, we have these 4 things, these Planck units: length, mass, time, and temperature. You cannot go any smaller than that. Everybody knows this, right? Energy equals mass times the speed of light squared. Einstein. John Archibald Wheeler, he's the guy who came up with the term black hole. 1989, he wrote a paper, Hit from Bit, expanding on this, showing that at the fundamental level, when you have quantum collapse and you have an observer make an observation, that is when it goes from a wave to a particle. And at the fundamental level, those Planck units are bits, and the bits that make up our whole universe. Gödel's incompleteness theorems, anybody heard of these? All right, good. So Gödel's really, really cool. In any sufficiently complex axiomatic system, there exists true statements that the system itself cannot prove. That means that there are no, or at least suggests that no cybersecurity system can be entirely self-contained or secure from within its own logic. The second incompleteness theorem, paraphrased, is that no system can prove its own consistency. It requires external validation. You cannot do it from the inside. You literally have to think outside the box. Does anybody know what this is? This is a Crookes tube. It's on one end you have a cathode, on the other end you have an anode, big battery, and you see that cross there in the middle, that's a barricade. And you're seeing electrons. That's a ray gun. That's what that is. So those are bits of both matter and energy. The same thing shooting down that tube. That's what it looks like. This is probably the simplest diagram you're going to find. You scale this up, you give it a really big vacuum tube. I mean, this is what neon lights are made of as well. But you scale this up, you give it a really big vacuum tube, like a really strong vacuum, and a really big power source. This is where you get X-rays from, like X-ray machine. And if you focus that lens, if you take a lens and you focus it, you get a bit stream and a magnet, and you can change the bit stream. So these are physical things that we're seeing right here. This is physical. This is how a CRT works. It just scans a whole bunch. So we're seeing a memory device right here. We're seeing a memory device that refreshes at 30 frames a second. This is a short-term memory device. So you have the electron coming in, it interacts with phosphorus in that screen, boom, it becomes a wave. It's a particle, it becomes a wave. And then it hits your eyes. And then it collapses back down to a particle again, goes down your optic nerve, boom, you've got something in your memory. This is physical. As an aside, Google and Harvard, they did a brain scan study, and they just published it like a couple of days ago. And the size of a tip of a pen, the amount of information here, 1.4 petabytes. A cubic millimeter. That is how dense our brain is. Those neurons and synapses and engrams. Engrams are where memories are physically stored in our brain. It's a physical phenomenon. That is part of my body. My memories are part of my body. Landauer's principle. The minimum theoretical energy consumption of computation. Erasing information is a fundamentally irreversible process. So information processing is not just a perceptual activity, it's thermodynamic. It is a one-way function, just like a cryptographic trapdoor. So, brief history of information security. Hieroglyphics. Who here knows that the ancient Egyptians actually had 3 different types of writing? This was only for secrets. This was only used by the priestly class. They had a phonetic alphabet. This is a skytele. Anybody heard of this before? All right, pretty cool. You take a long piece of tape, and I'm kind of leading into something here. You take a long piece of tape, you wrap it around a cylinder or a rod, and the diameter of the rod is your cryptographic key. And then you write on it, you have a message, spin it up, that's where your key comes out. Enigma. Cryptographic machines, you have a rotor there. And you've just got a couple of keys, so they just keep looping back in on themselves. This works the same way. Anybody ever used one of these? I have. Okay? Some older guys in here. This is how we used to fill crypto devices. We would get keys issued by the NSA that would come out on tape. And again, this is physical bits becoming stored in a medium. Right? There's rotors in there. Again, you pull the tape, and it turns into an electrical signal, and you're doing that same function. So, taking a step over to parameter security, failure, and zero trust. What do we learn about Gödel's incompleteness theorem? Right? The internet was not built to be secure. We're trying to bolt on security onto the internet. It's never going to work. It has to be designed from the inside out. It has to. We don't model complexity either, right? It was not meant. It is a complex system. It is a scale-free system. It keeps repeating. It keeps looping back on itself. So we're trying to fix this with zero trust, and it's good. It's better, right? We're doing microsegmentation, and we're modeling, and we're doing analytics, and we're putting taps on all our data streams, and we're trying to watch stuff. And it's a step in the right direction, but again, it has to be designed from the inside out. So how do we do that? We use DevSecOps. My friend Nick Shalon, he helped build this. Anybody here know Nick? I know at least one person in here. Really? All right. Anyways, he used to be the chief software officer of the Air Force. He worked with a couple of people, a big team actually. I think it was about 50 people, but they put this together. What you do is you've got an infinite loop, and you've got your tools, and your tools do automated security testing. And the releases to deployment are completely automated. You go from test to pre-prod to prod through automation. That means that you know what you're getting. That means that you have provable security as you deploy. So once we have that foundation, we can then apply digital twins. And digital twins are just what they sound. They are a representation of a thing in the real world that is virtual. Virtual replicas. In a good system, you're going to be able to have real-time data synchronization and predictive analytics. So, who here has heard of the next generation NGAD? Any Air Force guys in here? Next generation air dominance. So Will Roper, Will Roper used to be the chief of acquisition for the Air Force. And he wrote 2 incredible booklets. One is called Bending the Spoon. The other one is There Is No Spoon. And it's out on the Air Force's website. If you're interested, they're out there. So, we have digital twins now. What's the problem with digital twins? Stealing the file is stealing the thing. There's a lot of people who have real physical things that all they have to do is go and steal the file. So how do we get around it? You know, there was a talk 2 talks ago, and it said we've got to go layer 8, 9, and 10. We have to go not just technical, we've got to get in with people. And this cannot be top down. The internet is a scale-free system. That means that it's clusters and nodes that keep talking to each other. So it's a network within a network within a network, just like our brains. Our social systems are the same way. Our social systems have to mirror the internet. And they don't. And the internet have to mirror our social system. And they don't right now. There's a disconnect. Because we're trying to put a top-down hierarchy on a complex dynamical system. And it's a disconnect. It's literally schizophrenia. It's left brain and right brain. And it's a split brain. So I think the state guard idea of having that bridge is exactly where we would be. So, as a proposal to help address this, we have developed this security classification model that addresses things both from a top-down perspective and a bottom-up perspective. On the right, we have action, risk, and entity. And on the top, we have, everybody's done their security briefings, and they tell you sources and methods, right? That's not complete. We think this is at least somewhat of a high-level perceptual model that helps people be able to loop, right? Go back and forth, and near real time, just have a mnemonic where they can look at their program that they're on with their team and look, what actions am I taking? Or what actions are my team taking and the people I'm connecting with? Sources, intelligent sources and methods. Activities, so field exercises, right? Capabilities, what can I do? And then in the middle, we're in flux, vulnerabilities. And then at the bottom, this is all the stuff that's statutorily and by executive order classified at the federal level. There may be a few outliers, but this captures the most of it, right? Law enforcement, especially international law enforcement, right? Intelligence, operations, nuclear. Nuclear's unique because nuclear is it's a federal law versus executive order, so it's the Nuclear Secrets Act. And then state secrets, right? State Department, and then systems in general. Thank you so much for your time. Information is physical. War is physical. Information war is physical. Thank you so much. We are.